Okay, so in this video we're going to talk about constants, sums, and differences. So constants can appear in functions in two ways. One, they can appear alone. Say the function is a constant. In this case, the derivative is going to be 0. And why that is, well, let's do a little demonstration of why that is. So the derivative is the limit as h goes to 0 of f of x plus h minus f of x all over h. The function outputs c for every input. So the f of x plus h is going to be c, the f of x is going to be c. So we'll get the limit as h goes to 0 of 0, which is just 0. Another way constants can show up is as coefficients. So say we have a function which is c times some other function. The derivative is going to be c times the derivative of that other function. Again, let's show why this is true. So the derivative of f is going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. And what is f of x plus h? Well, that is c times g of x plus h. And f of x is c times g of x. And then if we factor out this c, remember the limit of a product is a product of limits, so we can factor out this c. We get c times the limit as h goes to z of g of x plus h minus g of x all over h. And that's the definition of the derivative of g. So we'll have c times g prime of x. Okay, so we have proved both these rules. Now let's do a couple examples. So first we're going to derive 8x cubed. Then we're going to derive 5 over the 10th root of x. Okay, there's a couple ways of writing the notation for taking a derivative of an expression. One, we could think of that expression as being a function, and then we can differentiate that function. So the 8 is a coefficient, it gets ignored. We take the derivative of x cubed, we get 3x squared, and then we multiply the 8 and the 3 and we get 24x squared. Another way of thinking about the derivative is it's a operator. Leibniz notation is good here. We're thinking of taking the derivative of 8x cubed. Again, the 8 is a coefficient, so it gets ignored. We take the derivative of x cubed, we get 3x squared, which results in 24x squared. All right, I'm going to use Leibniz notation for this next one. So the first thing I'm going to do is I'm going to rewrite this expression and rewrite the 10th root as x to the 1/10. And then I'm going to move it upstairs using exponent rules, turning it into negative 1/10. And then I'll just use the power rule. So we'll get 5 times negative 1/10 x to the negative 1/10 minus 1, which we can rewrite as negative 1/2 x to the negative 11/10, or negative 1 over 2 x to the 11/10. Okay, let's move on to our next rule. So our next rule is the sum difference rule. It goes like this. If f of x is the sum of two functions, call them u and v, or the difference, then the derivative of f is the sum or difference of the derivatives of u and v. Okay, let's do a quick example here. Call this example 2. So let's derive two functions. The first we call f, and it is going to be defined as x to the fourth minus 3x cubed minus 6. And the second is called g, and it is going to be 3x squared plus 1 all over x. All right, so when we take the derivatives of these things, we're going to take the derivative of each term and then add or subtract them in the way that they were added or subtracted in the original function. So the derivative of this x to the fourth minus 3x cubed minus 6 is going to be 4x cubed, the derivative of the first term, minus 9x squared minus 0. To take the derivative of the second function, I need to write it as a sum or difference. So the first thing I'm going to do is divide both terms in the numerator by that denominator. That's just a property of fractions. Now I can simplify. All right, so now I'm ready to take the derivative. The derivative of 3x is 3. The derivative of x to the negative 1 is negative x to the negative 2, which I can rewrite as 3 minus 1 over x squared. I hope you found this video useful.